So, welcome students to the next class of Introduction to Nonlinear Optics and Application. So, in the last class we started the evolution process inside the DRO. So, this is lecture number 14. So, we will continue this topic. So, DRO, the process of the DRO. So, again go back to the slides and we will find this relationship. This is a schematic figure of optical parametric oscillator, and this optical parametric oscillator schematic figure in the left hand side is shown how the singly resonant oscillator is working. That one wave of the frequency omega s is oscillating inside the cavity, and as a result we will get one amplified wave which is omega s. And in doubly resonant oscillator, two different frequencies, signal and idler, both resonates. So, these two are simultaneously resonate. So, since this is resonate simultaneously, we need to find out what is the threshold condition. So, today our goal is to find out the threshold condition, and in the singly resonant oscillator we have the gain like this. So, the threshold gain we figure out in terms of the cavity length and the reflectivity of the two mirrors, and we have this expression in our hand. And also in the previous class we find what is the round trip, after round trip what is the expression of the field and with respect to the input field for two field Es and Ei. So, this is the expression we derived last day with the reflection matrix and the corresponding propagation matrix. This is a propagation matrix where A, B, C is represented in this term. So, in order to do that, what we need to calculate, what we have calculated, that we solve the differential equation of Es and Ei, and the field is now going from here to here, and we find out what is the general form of the E for Es and Ei. So, just solve the differential equation so that it becomes a function of Z. After reflection it goes back, and when it goes back there is no change of the field because the phase matching is not there. So, unit matrix is associated and the reflection matrix is associated because there is a reflection, and when it comes to this point again it will be reflected for the next mirror to start the next trip before starting the next round trip. So, this reflection basically gives basically given by this matrix. So, we have 4 matrix together, and once we have 4 matrix together, then this 4 matrix can combine and we can generate the relationship between the input and the output field, and then we find what is the threshold condition to amplify the process. Well, for DRO, if I go back and multiply all these matrices to make it more concise, then if you do, we will find this matrix form. This is the compact matrix for round trip. So, we will have one field here at this point and this point. After making a round trip, what should be the value of the fields, what should be the functional form of the field of Es and Ei together can be represented by this matrix, this master matrix. So, now once we have this matrix in our hand, so we can have a relationship between Es and E0 and EIZ and EI0. So, ESZ ES0, this from this relation we can have the condition of gain for Es. In the similar way I can have the condition for gain of Ei also. And what is the condition of threshold condition for gain? The threshold condition for the gain is after making a round trip, the value of this field at least should be equal to whatever the value we have at the starting point. So, if the loss is introduced, then obviously because of the loss this field will having a reduced amplitude, we will have amplitude which is reduced, but right now the loss is not there. Even if the loss is not there, after making one round trip, it is essential to find out what should be the value of the field at Z should be equal to the value at input. So, after making one round trip, if these two fields are at least same, we can say this is at least the condition where we should have some kind of amplification. So, greater than these things will be amplification, equal to these things is the threshold condition. So, now we know this quantity ESZ EIZ star round trip is nothing but this matrix form. This is the condition, or this is the expression that we have derived, that should be equal to this value ES0 EI0 star. Now, ES0 EI0 star, and from this expression I can now have here A RS minus 1 B. So, if I make it this side and then make the related algebra, I will have an expression something like this. So, this matrix expression suggests that if I need to have a non-trivial solution, then the determinant of this quantity has to be 0. So, what we are doing? We have a round trip expression in our hand. From this round trip expression, we can try to find out the relationship between the field that is at z equal to 0 and the field at round trip. So, round trip expression in our hand, and once we put this condition same, that is our threshold condition for amplification of the input field, and this threshold condition is represented by this. So, if I solve this equation, then I will get one information, but without solving, even solving, we have a condition to have the non-trivial solution. The condition of the non-trivial solution, as I mentioned, if these two are non-zero, then this equation will satisfy once the determinant of this quantity is 0. So, determinant of this matrix, basically determinant of this matrix is 0. So, once the determinant of matrix is 0, now is the time to calculate what is going on. So, we calculate the determinant simply. So, AR this multiplied by this cross multiplication minus this cross multiplication is equal to 0. ARS minus 1 DRI minus 1 minus CBRS R1. But you should remember what is the value of A, B, C and D. These are the matrix elements, and these values of these matrix elements are already calculated. So, these are the matrix element that is in our hand. So, what we do right now? So, we make RI RS common from this expression to this expression, and I will have AD minus BC. So, AD minus BC, if I see carefully, AD is this quantity. So, AD is nothing but cos hyperbolic of GZ, which we have here, and since it is a threshold condition, because I am making a threshold condition, I equate the equation under threshold condition. So, I write G threshold here, because whatever the value of G we are going to impose is basically the threshold condition of that. Now, if I try to find out what is my BC, so BC is I multiplied by I minus I, it will give me 1 root over of kappa s kappa I multiplied by root over of kappa s kappa I. So, it will once again give you 1 sine hyperbolic multiplied by sine hyperbolic, it will give me sine hyperbolic of square GZ. So, BC is simply sine hyperbolic square of ZZ. So, AD minus BC is simply cos hyperbolic square G threshold L minus sine hyperbolic square G threshold L. So, cos hyperbolic square minus sine hyperbolic square, we know cos hyperbolic square x minus sine hyperbolic square x is nothing but 1. So, we will have a more simplified expression by just putting this is equal to 1. So, expression is now simplified. It looks cumbersome, but when I calculate all this relationship is there. So, we will have this expression. Also here we have D and A are same. So, I can write RS RI D and A, if I take common, then it should be cos hyperbolic. It should be cos hyperbolic if I take common D and A. So, RS RI multiplied by cos hyperbolic plus 1, that will be our expression here. RS RI minus cos hyperbolic RI RS plus 1 is equal to 0 is our expression. So, from this expression we can readily see that I can have a value of G threshold. So, I can have a value of G threshold in terms of RI and RS. However, cos hyperbolic G threshold L is a series function. So, we need to make some kind of approximation that we eventually do, and we will come to that point what should be the value of G threshold. So, cos hyperbolic G threshold from this expression I can write is 1. If I write this and try to solve what is cos hyperbolic, then I can by simple algebra I can find that it is 1 plus RI RS divided by RI plus RS, because if I write, it should be cos hyperbolic G TH L multiplied by RI plus RS is equal to 1 plus RI RS, and then cos hyperbolic L is RI RS divided by RI plus RS. Now, RI and RS are very close to 1, because this is the reflectivity of the mirror of two frequencies, and it has to be very strong or very high value. So, these are nearly equal to 1. Since this is nearly equal to 1, RI should be nearly equal to 1, RS should be nearly equal to 1. So, RI multiplied by RS is nearly equal to 1. So, this entire quantity should be nearly equal to 1. So, cos hyperbolic L is nearly equal to 1. So, that means I can make an expansion of cos hyperbolic. So, cos hyperbolic expansion I will go up to second term, because this is possible when the threshold value of the G or whatever the G is comparatively small, and if I expand this, we will have 1 plus half G threshold L square, which is the expansion of this 1. So, here we make another this is 1 plus G threshold square. So, cos hyperbolic. So, now from this expression what we try to do, we try to find out what is the value of G threshold. So, cos hyperbolic G threshold L is equal to this quantity. It is difficult to find out what is the G threshold in a compact form. So, that is why we make this expansion. So, after making the expansion, we have half G threshold L square is equal to 1 minus RI RS divided by RI plus RS minus 1. So, that quantity basically give rise to one simple expression 1 minus RI multiplied by 1 minus RS divided by RI plus RS. If you make the simple algebra, just put it here, RI minus RS will be here and take common, then you will get this result readily. Now, again RI and RS are very close to 1, because they are the reflectivity of the two mirrors of two different wavelengths, and this reflectivity is very strong. So, very strong means here they are very nearly equal to 1. So, RI plus RS is nearly equal to 1, that means this RI plus RS is equal to 2. So, I can replace these things equal to 2. So, if I make this approximation, G threshold, this 2 and this 2 will cancel out. So, G threshold simply becomes 1 by L root over of whatever the quantity we have. So, finally, we have an expression of the G threshold for doubly resonant oscillator, and for doubly resonant oscillator we find the expression in terms of RI and RS. These are the refractivity of the mirror for the signal and idler. After having the expression, next thing we will going to compare the expression that we have for SRO, and if I write these two together. So, these twos are expression of the threshold of G at DRO and the threshold of SRO, and if I find these two expression, then we can simplify a little bit, because in this case we can see that Ri and Rs is closely equal to 1. So, I can simplify, but our goal is to find out what is the ratio of the threshold value of DRO and SRO. So, now we will going to simplify this. As I mentioned, I write Ri and Rs is equal to Ri, R1 and R2 is equal to Rs for single resonant oscillator, because in single resonant oscillator only omega s will going to oscillate. So, I can write the reflectivity here as omega Rs and Rs instead of writing Ri and Ri. So, Ri and R2, R1 and R2, this is R1 and R2 in the previous notation. Now, I just change, because these two are very close to each other and same as Rs. So, if I do, then this expression becomes root over of 2 L 1 divided by Rs minus 1, or root over of 2 divided by L, and then R 1 minus Rs make a root and root over of Rs. So, once we have the expression, a little bit simpler expression, then we are now in a position to make a ratio of G threshold DRO and G threshold SRO. When we make a ratio, then 1 divided by R root over of these things and 1 L divided by root over of this. So, these things 1 minus Rs and 1 minus Rs root over of these two things will cancel out, L will cancel out, root over of Rs will be there. So, root over of Rs by 2 and these things will be there, but Rs is nearly equal to 1. So, I can write this nearly equal to 1. So, we will have one expression something like this in our hand. This is the expression making Rs equal to 1. So, these are the ratios, these are the two SRO and DRO, and we have the ratios here, and this ratio suggests that it will be 1 minus Rs Ri divided by root over of 2. So, now G threshold is proportional to the intensity of the pump, that we know. G threshold is proportional to the intensity of the pump. Since it is proportional to the intensity of the pump, so what we will do, that we make a square of that, so that this ratio became the ratio of the power of DRO, or the ratio of the intensity of the DRO versus SRO, and this intensity is the threshold intensity to have the amplification. So, need to find out what should be the ratio of the threshold intensity of these two quantity, and the right hand side we find 1 minus Ri by 2. So, now you can see that Ri is a refractive index, Ri is a reflectivity coefficient, and this reflectivity coefficient for this field Ei or the frequency omega I, it should be very close to 1. So, if this quantity is very close to 1, the numerator is very small. If the numerator is very small, we can readily see that the threshold value of the DRO is much less than the threshold value of SRO. That means, the power required to excite the amplification in SRO is much greater than the power required to excite the amplification in DRO. That is an important conclusion that we have. So, we can put the some value also, say if Ri is of the order of 0.98, which is very close to 1, then 1 minus Ri is 1 minus 0.98, it is 0.02, and now it is divided by 2. So, I threshold for DRO and I threshold for SRO becomes 0.01. So, that means the power required to excite or the power required to amplify in SRO is much less than power required to DRO is much less than the power required to SRO. But there are few drawbacks in SRO in DRO also, even though the power required for amplification in DRO is much less, but there are some other issues. So, let me describe these issues before the conclusion of this class. So, in SRO what happened, these are the modes, the allowed modes, this is interesting. So, in SRO we have these are the allowed modes represented by the vertical lines in omega axis, in the frequency axis, and these are the allowed modes, and what are the allowed modes can be figured out with this expression. For these allowed modes, the question is which should be really resonating. There are many modes, all these things are there. So, that means if I draw different modes, so we have this is one mode, we have another modes, we have another modes and so on. These are the different modes that we can have. This is the schematic picture to show how this mode can look like. But the question is, among these modes, which mode will really resonate inside the system, which mode will basically amplify, or the which corresponding frequencies amplify, because all cases we will have. So, omega p is divided to two frequencies, omega s and omega I, and the relationship is omega p is constant. So, omega s plus omega I has to be constant, but there are infinite way that omega I and omega s can constant. So, omega s can have different values, and these different values are nothing but these different modes as well as omega I, but their summation is constant. So, if I consider only one case in SRO for where we have one condition, one resonating condition. So, this dotted thing is the gain curve of the system, because this resonator should have some kind of gain spectrum. It will not going to amplify all the frequencies depending on the value of delta k. If delta k is not equal to 0, then we have a gain figure, a gain bandwidth that we have already discussed in our previous classes. So, the mode which is close to the maxima of the gain curve will basically going to oscillate, and this is shown by this red dotted line. Red dotted circle basically gives you the identification of the modes that will going to vibrate or that will going to resonate in SRO. Corresponding frequency spacing is also shown. These are the modes that all are allowed modes in the SRO. In DRO case, on the other hand, instead of having one modes, instead of one frequency, we have two frequencies that are going to resonate. So, omega s and omega I are the two frequencies that will going to resonate, and if it is resonating, these two frequencies are resonating, then it is not necessarily the modes that in having a maxima will going to vibrate. That is the interesting point here. So, now what we will do? So, omega s, these are the allowed modes, and omega I, these are the allowed modes. Because the spacing is different, it will not fall one by one. So, you can see that there is a mismatch between these 2 points, these two frequencies gradually, but there is a possibility that they will again make a similar, they will again coincide a similar point here. So, these are the two modes where these two values are coinciding to each other. In this case, omega s is increasing, and in this case omega I is increasing. Why it is? Because if I increase the omega s, omega I has to be reduced, so that the summation of these two become constant. So, that is why if this is in forward direction, it is backward direction, it is reducing, and the frequency spacing is also represented here, which is pi c divided by NIL. But the interesting thing is they will going to resonate where these two modes are overlapping to each other. It is something like a Vernier scale kind of stuff. So, these two are the corresponding modes which are overlapping, and these two are vibrating. But please note that it may not be necessarily the modes that is at the highest gain value. So, gain value is less, but still it will going to oscillate at this particular points, or this for these two modes it will going to oscillate. So, since this is a very critical condition. So, it is the stability of the DRO is really very critical. So, even though there is an advantage of the DRO that we have less threshold power to amplify the signal, but the problem is here if I want to amplify the signal and the corresponding idler. So, the corresponding frequency modes will need to be coincide like this, and they will only then only they will going to vibrate. So, this condition is very critical condition. So, the stability issue will be always there in DRO. So, well students, so let me conclude today's class here. So, today we have learned detail about the operation, how the operation can done in the DRO system, in DRO amplification system, and we find that in DRO we have less threshold power required to amplify compared to SRO, but there are some critical issues in DRO regarding the resonance frequency. So, the resonance frequency had to be coincide for omega s and omega I, then only it will resonate, and not only that, the resonance frequency, the location of resonance frequency may not be in the peak point of the gain curve. So, that is why the efficiency, eventually the efficiency is not be that much, and also the criticality should be there. So, it is very difficult to handle with this DRO system. Anyway, with this note, let me conclude here. So far we are discussing about the Chi2 effect. So, the Chi2 effect phenomena is almost complete. So, in the next class we will going to start a new brand new topic which is related to Chi3, a higher order nonlinearity, different kind of phenomena will be there. So, with this note let me conclude, and thank you for your attention, and see you in the next class.